What if the ocean isn't destroying our structures, but secretly making them stronger? Hidden inside 2000-year-old Roman harbors is a chemical mystery modern science still struggles to copy. This is not just history, it's a breakthrough for our future. Subscribe now to uncover the lost science that could change how we build forever. Part 1: The Modern Engineering Paradox. What if the ocean, the very force we fear most, is not destroying some structures, but actually making them stronger? Today, modern concrete is everywhere. It builds our cities, bridges, ports, and seawalls. It holds up the systems that support billions of people. But there is a serious problem hidden inside this material. Most modern concrete used in marine environments begin to fall within just 30 to 50 years. Salt water slowly seeps into the concrete. Inside steel bars begin to rust. As rust expands, it creates pressure. Tiny cracks form. Over time, those cracks grow larger. Eventually, the structure weakens and breaks apart. Engineers around the world are fighting this constant battle. Reports estimate that corrosion of reinforced concrete costs the global economy more than $2.5 trillion every year. Now, here is where the mystery begins. Along the coast of Italy, beneath the waves, ancient Roman harbors still stand. These structures are nearly 2000 years old. They have faced storms, earthquakes, and endless exposure to salt water. Yet they are still there. In places like Baiae and Pozzoli, researchers have studied these ruins closely. What they found was shocking. The concrete is not falling apart. In fact, in many cases, it is stronger today than when it was first built. This completely contradicts modern engineering knowledge. Seawater is supposed to damage concrete, not preserve it. So, how is this possible? What did the Romans understand that we have forgotten? Scientists began to search inside the ancient material. They broke samples apart. They studied them under microscopes. They analyzed their chemical structure. And then they found something unusual. Mixed into the concrete was a strange grey material. It was not ordinary sand. It was not just crushed stone. It came from a volcanic region near southern Italy. This material would later be known as pozzolanic ash. At first, it seemed like just another ingredient, but the deeper scientists looked, the more important it became. Because Roman concrete does not behave like modern concrete. Modern concrete hardens once and slowly weakens over time. Roman concrete does something different. It continues to react long after it is placed in the sea. It changes, it evolves, it grows stronger. Instead of breaking down, it rebuilds itself from within. This raised a powerful question. Could the ocean itself be helping these structures survive? Could seawater, instead of being an enemy, actually be part of the solution? To understand this, we must follow the Romans back to the source of their material. Not to a workshop or a factory, but to the slopes of a volcano. Because the secret to their strength was not hidden in stone, but in ash. Part 2: The Alchemy of Pozzolanic Ash. To understand the strength of Roman concrete, we must go to southern Italy near a powerful volcano called Mount Vesuvius. This region is covered in volcanic ash. Long ago, eruptions spread this ash across the land. To most people, it looked like dust from destruction, but to the Romans, it became a valuable resource. Today we call it pozzolanic ash. This ash was very different from normal sand. It contained tiny particles of volcanic gas. These particles were rich in silica and aluminium. These two elements are very important in chemical reactions. Roman engineers discovered something special. When this ash was mixed with lime and water, it did not just dry like modern cement, it reacted. This reaction created a strong binding material. It could hold stone together even underwater. The Romans quickly realized its potential. They began using it to build harbors, piers, and breakwaters. Historical records show that Roman builders poured this mixture directly into wooden molds placed in the sea. The concrete hardens in place, forming massive underwater structure. But here is the key detail. The hardening process was not the end. In modern concrete, once it sets, the chemical reactions mostly stop. Over time, the material slowly weakens. Roman concrete behaved differently. Because of the volcanic ash, the material stayed chemically active. Inside the hardened concrete, tiny particles of volcanic glass remained. These particles did not fully react at the beginning, they waited. This created a kind of delayed reaction system inside the structure. At first, Roman builders may not have fully understood the science, but they clearly saw the results. Their structures lasted longer. They resisted waves and storms better than other materials. Over time, they trusted this method. They built entire ports using this formula. But the most important moment came after construction. When the concrete was placed in seawater, something new began to happen. Water slowly entered the tiny pores inside the material. It reached the unreacted volcanic particles. And that is when the real transformation started. The seawater did not destroy the concrete, instead, it triggered a new chemical process. The volcanic ash began to break down in a controlled way. It released silica and aluminum into the surrounding structure. These elements started forming new minerals inside the concrete. This means the material was not finished when it hardened. It was only beginning its long transformation. The Romans had unknowingly created a system where nature continued the construction process. The ocean became part of the design, and this leads us to the next stage of the mystery. The exact moment when seawater enters the concrete and turns it into something even stronger. Part 3: The Seawater Catalyst. The real secret of Roman concrete begins after it is placed in the sea. At first, everything looks normal. The mixture of lime, volcanic ash, and rock hardens into a solid mass. The structure appears complete, but inside, something important is still waiting. Roman concrete is full of tiny pores. These are very small spaces within the material. In modern concrete, pores are a weakness. Water enters, damage begins, and cracks grew. But in Roman concrete, pores serve a different purpose. They act like pathways. When seawater touches the surface, it slowly moves through these tiny channels. It travels deep into the structure. This is the moment where modern concrete would begin to fail. But here, something completely different happens. The seawater carries dissolved minerals. It contains ions like sodium, magnesium, calcium, and potassium. These ions enter the concrete and reach the volcanic ash particles trapped inside. Many of these particles are made of volcanic glass. This glass is unstable over long periods, especially when exposed to water. So it begins to dissolve. But this is not damage. This is a controlled chemical process. As the volcanic glass dissolves, it releases silica and aluminium into the surrounding water inside the concrete. Now the system changes. These released elements do not disappear. They begin to react with calcium from the lime. This creates new chemical compounds. These compounds slowly grow into solid mineral structures within the concrete. This process continues for years, even centuries. Instead of weakening, the internal structure becomes more complex and more tightly bonded. Scientists studying samples from Roman harbors have confirmed this process using advanced tools like electron microscopes and X-ray analysis. They found that the interaction between seawater and volcanic ash is the key driver of this transformation. In simple terms, seawater is not acting as a destructive force, it is acting as a catalyst. A catalyst is something that helps a chemical reaction happen faster or more efficiently without being used up. The ocean is constantly feeding the reactions. It supplies fresh ions, it keeps the system active. This means the concrete is never truly finished. It continues to change, adapt, and strengthen over time. This idea is very different from modern engineering. Today, we design materials to resist the environment. The Romans did something smarter. They designed a material that works with the environment. The sea is not the enemy, it is the part of the structure. And this ongoing research and reaction leads to the formation of something very rare, a mineral that grows inside the concrete like a natural reinforcement system. A crystal that can lock the structure together at a microscopic level. To understand how Roman concrete becomes even stronger over centuries, we must look at the birth of this mineral, the formation of al-tobermorite, a crystal that may hold the key to building structures that last for thousands of years. Part 4. Birth of the al-tobermorite crystal. Deep inside Roman concrete, a quiet transformation continues for centuries. As seawater moves through the pores and volcanic ash slowly dissolves, new minerals begin to form. Among them is one of the rarest and most important discoveries in modern materials science. It is called al-tobermorite. This mineral does not form easily. On Earth, it usually requires very specific conditions such as high temperatures and controlled chemical environments. That is why it is rarely seen in nature. Yet inside Roman harbor concrete, it appears naturally. Scientists studying samples from ancient sites like Pozzuoli and Baia have found tiny crystals of al-tobermorite growing within the material. These crystals form over long periods, sometimes taking decades or even centuries to develop fully. But what makes this crystal so special? Al-tobermorite has a strong layered structure. At a microscopic level, it looks like thin plates stacked together. These plates can interlock and spread throughout the concrete. As they grow, they fill small cracks and empty spaces. In modern concrete, cracks are dangerous. Even tiny fractures can expand over time, allowing more water to enter and cause further damage. But in Roman concrete, cracks become sites of repair. When a small crack forms, seawater enters. It carries minerals into that space. Chemical reactions begin again. New crystals start to grow inside the crack. Slowly, the crack is filled. This process acts like a natural healing system. Instead of weakening, the structure becomes stronger. Researchers using electron microscopes have observed these crystal networks. They found that tobermorite forms a dense web inside the concrete. This web connects different parts of the material, increasing its overall strength. In some cases, these ancient structures show better resistance to future than modern marine concrete. Even more surprising, these harbors have survived natural forces that should have destroyed them long ago. Italy is located in an active tectonic region. Earthquakes and ground movements are common, yet many Roman harbor structures remain stable. The crystal growth inside the concrete helps distribute stress. It prevents sudden failure. It gives the material flexibility along with strength. Today, as climate change raises sea levels and increases coastal erosion, engineers are searching for better solutions. Modern sea walls require constant repair. They are expensive and often temporary. But Roman concrete offers a different idea, a material that grows stronger with time. A material that works with seawater instead of fighting it. Scientists in 2026 are now trying to recreate this ancient formula in laboratories. They are studying volcanic ash, seawater chemistry, and mineral growth. The goal is to build sustainable, long standing coastal structures. Structures that could last not just decades, but centuries. The answer to the future may not be new technology. It may be ancient knowledge hidden in volcanic ash, waiting for us to understand it again.